So now we're going to talk a little bit about horizontal asymptotes. So horizontal asymptotes are when we look at a rational expression, something like, let's say I've got a graph like this, and when I graph my rational expression, I might see something like this. We know that the vertical break in the graph right here, this is called a vertical asymptote. And the horizontal break in the graph, this one right here, this is called the horizontal asymptote. Note the equation for the horizontal asymptotes are going to be y equals something. The equation for vertical asymptotes are going to be x equals some number. Okay? Now we're going to talk a little bit about how we find horizontal asymptotes. So the first step is given a rational function, p of x over q of x. So let me give you an example, something like x squared plus 5x plus 6 over 2x minus 5. The first thing that we want to do is find the degree of p of x and q of x. So in this case, the degree of the numerator would be 2, and the degree of the denominator would be 1. Now, I'm going to erase this, and we're going to look at the three different cases, because these degrees, either the top one's greater than the bottom one, or the bottom one's greater than the top one, or they have degrees that are equal. And depending on these situations, we're going to have different things happen for our horizontal asymptote. So if the degree in the top is less than the degree in the bottom, so if degree of p of x is less than q of x, let me give you an example of that. Something like x squared plus 5x plus 6 over x to the third power. This, so you can see the degree on top is 2, the degree on the bottom is 3, the degree on the top is less than the degree on the bottom, then the horizontal asymptote, which I'm going to abbreviate HA, is at y equals 0. And let me pull up a graph of this so you can see what I'm talking about. So if I pull up a graph of this, if you take a look, as I kind of look at these points, do you see that the y values are getting really, really close to 0 but never actually touch it? That is how we know. And again, if we go out further, we can see that again, these y values are really, really small, but they're not actually equal to 0. It's going to get really close to that line, but it never actually hits 0 there. Okay? If the degree of p of x is equal to the degree of q of x. So let me give you an example of this. If I have something like this, x minus 5, x plus 3, over x minus 2, and x plus 1, this will actually have a horizontal asymptote at, so the degree on top is 2, the degree on the bottom is 2. We have to look at the leading coefficients, and the horizontal asymptote would be y is equal to the leading coefficient on top over the leading coefficient on the bottom. To make this a little bit more clean, I'm going to go ahead and so you can see this example a little bit better, I'm going to make this 2x minus 5. So it's a little hard when it's in completely factored form, but we can figure this out. If I multiply the first two terms, 2x times x is going to give me 2x squared. And if you want to FOIL it the rest of the way out, that's fine, but you're going to get a leading term of 2x squared. And when I FOIL out the stuff on the bottom, x times x is x squared, and then you're going to FOIL the rest of it out, and you're going to get stuff. Okay? What is the leading coefficient of the numerator? Well, the leading coefficient of the numerator is 2. And what's the leading coefficient of the denominator? Well, there's a 1 in front of the x squared, so the leading coefficient in front of the in the denominator is 1. So we know this has a horizontal asymptote at y equals 2. And let me pull up a graph and show you that. So I'm going to take this right here, I'm going to put it into a graph, and you can see that there is a horizontal asymptote, and if I zoom in a little bit, you can see what is that y value. As I go out, it's going to get really, really close to 2. Let me actually zoom this way in here. If you take a look, as I look at these y values, you see they're getting really, really close to 2, but they never actually touch 2. Same on the other side. As I go out, you can see this is right below 2, and it's going to get really close to it, but it's never going to actually touch 2. All right, so the last one is if the degree of p of x is greater than the degree of 2 of x, or q of x. So there's actually a special case with this one. I'm going to make a little bit of room. So if p of x is greater than q of x, then there is no horizontal asymptote. Let me give you an example of this one. Something like this. Y is equal to let's say x to the 5th over 2x minus 1. If I type that in, and if I look at that graph, let me fix these scales a little bit. Look at what's happening. You see these are just going crazy on the edges. This is just, as this goes up, these are going up forever. So that does not have a vertical asymptote at all, right? These are just shooting up to infinity. But there is this special case. If the degree of p of x is 1 greater than q of x, then there's an oblique asymptote. And let's take a look at what that looks like. So if I have, I'm just going to pick a very easy one, x squared minus 5x plus 6 over 2x plus 1. How we find an oblique asymptote is we do long division. So we're going to do x squared minus 5x plus 6, and we're going to divide that by 2x plus 1. This is going to be a little tricky, but 2x, I want to get to x squared, so I'm going to actually multiply by 1/2 x. This is going to be really ugly, but that's okay. 1/2 times 2x is 1x. 1/2 times 1 is positive half x. And then don't forget we have to change these signs. So this becomes minus, and this becomes minus. Sorry, that should be an x squared. And then these are going to cancel. And then 5x minus 1/2 x is negative 5.5x. And then we're going to bring our plus 6 down. Oh, great. 2x, and I want to get to 5.5x. All right, how I'm going to figure out, I have 2, I want to get to 5.5. What I'm going to do is negative 5.5 divided by 2, which gives me 11 over 4, negative 11 over 4. So I'm going to multiply by 11 over 4, and that sounds crazy, but negative 11 over 4 times negative 2 gives me negative 5.5x. And then negative 11 over 4 times 1 is minus 11 over 4. Now here's what's nice. You can work this out. This becomes plus, this becomes plus, this works out, and you're going to get 35 over 4 for my remainder, but we don't really care because this is our oblique asymptote. So our oblique asymptote is y is equal to 1/2 x minus 11 over 4. Let me show you a graph of that real quick. Okay, so you can see I've graphed my function right here. You can see it's got this kind of slanted axis, and then here is my oblique asymptote. Again, you can see that's what I got right here when I did that long division. I'm going to turn that on and just see how it matches up. Again, it doesn't match it up exactly, but as I go out, it's really looking like it's getting really close to that oblique asymptote. So that's how we would find the oblique asymptote is doing long division. Again, if the numerator is, if the top is less than, it's 0. If the degrees are equal, then you do the leading coefficients. And if the degree is greater than, there's no horizontal asymptote, but check for that special case where you might have an oblique asymptote.